first talk will be some of the product of the recursive programs for hypersafety verification by the Ruotong Cheng from University of Toronto.
Thanks for the introduction. Let's look at this recursive program that computes integer division. Stating and proving its partial correctness require nonlinear integer arithmetic. Alternatively, we can state properties that relate multiple executions of div, such as scaling. When n at least doubles, div at least doubles. It is an instance of hypersafety properties. Specifically, a k-safety property is a property whose violation is witnessed by k finite length program runs. Hypersafety is k-safety where the arity k is greater than 1. The expectation is that we can prove hypersafety properties without having to prove partial correctness first. It's well known that hypersafety verification can be reduced to one safety verification by constructing a product program. Self-composition is the first product construction proposed. For k-safety, it makes k disjoint copies of the input program, p1 to pk, and concatenates them. For iterative programs, the problem of product constructions is somewhat well studied, and there have been many of them. The question we ask in the paper is, what are product programs for hypersafety of recursive programs? To answer this, we first need to understand why we need more than one product construction. Let's recall the scaling property. We make two copies p1, p2. With self-composition, proving safety requires guessing an inductive summary of div that must be nonlinear. Consequently, existing provers cannot establish the safety automatically. We can also argue running the two copies in lockstep doesn't really simplify the proof. Conceptually, to avoid nonlinear reasoning, we need a variation of lockstep that matches every two calls of p1 against one call of p2. But what if the constant 2 is changed to 3 or 4? Or even a property that looks more different, such as distributivity? It's intuitively clear that all these need different product constructions. Thus, recursive programs inherit from iterative programs the complication of needing a universe of product programs. In addition, they have a new challenge. For that, let's recall the concept of interprocedurally realizable paths. Such paths of P1 are illustrated here and can be produced by a context-free grammar. We use round brackets to denote calls and returns, and those for internal actions. By definition, the brackets are balanced. Similar for P2, except that we use square brackets to differentiate from the first copy. Suppose we want to prove the version of scaling with constant 1. Let's interleave in lockstep tau1 from P1 and tau2 from P2, both making two function calls. We can alternate between the statements from the two copies in the naive way, which leads to a mismatching between the types of brackets. This cannot be a run-of-one recursive program, and we will not be able to leverage existing techniques for safety verification of recursive programs. Formally, the set of all such interleavings is not a context-free language. However, a small twist is sufficient to make this example work. At the returning phase, we may as well start the alternation with P2. Then, this does look like a run-of-one recursive program. And we have a generalizable proof in linear integer arithmetic. Let's go back to this picture of using product programs for hypersafety verification. We have seen that when the input program is a recursive program, the construction should be expressive, closed under the class of recursive programs, sound, and efficient. Since soundness is so critical, we look at it first. Given a run, swapping adjacent letters from disjoint copies do not affect the overall semantics. We may repeat this operation any finite number of times, which still preserves the overall semantics. Then, all possible interleavings are divided into equivalence classes according to whether they can be rewritten to the same run. note that we identify PI with its realizable path. The shuffle operator here is just the shuffle of languages. For a set L of interleavings, a reduction of L is defined as a subset that contains one representative from each commutativity equivalence class. We have that any reduction of the shuffle is safe if and only if the input program is hypersafe. Therefore, to guarantee soundness, we can construct reductions as product programs. But how do we select one reduction, such as lockstep, out of the infinitely many? For that, we introduce a scheduler, which conveys the user's idea of the reduction. As expected, the maximal product can be the shuffle. The scheduler then guides the construction of the reduction of the shuffle. It does so by giving the preference for the next statement based on the partial run so far, which is mathematically a function from partial runs to total order on the statements. We call it a contextual order, and the reduction induced is a contextual X reduction. Schedulers formalized as contextual orders lead to this picture, but it's problematic in two ways. A general contextual order is not really describable, and the output doesn't satisfy the closure property that we mentioned. To solve these problems, it's first important to understand when can a reduction be viewed as a classical recursive program. Intuitively, it means two things. The reduction should be finitely representable, and each run should be able to be simulated on a single stack. This needs to be made formal. The representation should be able to express the realizable path. For better theoretical properties, we use visibly pushdown automata and grammars. The languages they induce, VP-else, form a subclass of context-free languages. Moreover, we require each run to be well-nested, which I will explain. A run row in the shuffle is called well-nested if any matching call and returning row belongs to the same PI. For example, these are ill-nested, whereas these are well-nested. But why is well-nestedness sufficient? This is because a well-nested product program can be reinterpreted as a classical recursive program in a formal sense. By default, the product operates on a k-tuple of stacks, but we can also view it as operating on a stack of k-tuples. We can prove for all well-nested partial runs, this shift of semantics doesn't affect the validity of any Hoare triple. With a little effort, one can find a set of conditions on the contextual order to make everything work out theoretically. However, in addition to the natural requirement that the order is VP representable, there is an extra condition, which we call coherency, which places extra burden on the user to check. Thus, we consider an alternative path. We define a new shuffle operator, the well-nested shuffle, as the shuffle restricted to well-nested runs. The good thing is, reductions of the well-nested shuffle are by definition well-nested. Note that the well-nested shuffle is not closed under commutativity. The constructions in the literature do not reduce a non-closed language for technical reasons, but in this case, we managed to put this out. And the result is, if the contextual order is VP, this reduction is also VP. The proof goes by linking to the coherency condition and using this very nice property that VP-else are closed under well-nested shuffle. Thus, we go from this picture to this. But can we go further? It would be great if the user doesn't need to specify their reduction idea at all. That is, the algorithm searches for a reduction and the proof at once. But that turns out to be not scalable, especially for recursive programs. So instead of eliminating this description completely, we try to allow a simpler description, trading expressivity for user friendliness. Let's revisit the properties we've seen so far for the div example. We can identify some basic building blocks. Scaling uses a variation of lockstep, where the first copy runs s times as fast as the second copy, depending on the constant S. As for distributivity, we can write the reduction as the composition of two reductions, O plus and O times. Intuitively, O plus should be a sort of concatenation, but this is different from self-composition. We should nest the second copy fully inside the first copy, and lockstep the result of this with the third copy. We call the new concatenation operator nested concatenation. These building blocks are all formalized in our paper. Then we introduce canonical reductions as all combinations of the building blocks. The key result is that applying any building block to the wall nested shuffle gives a contextual lex reduction induced by a VP order. So canonical reductions can be connected to the lex reductions that we have defined. We implement our method as a tool called Hypersafe. Let's look at some of these components. When the reduction idea is given as a canonical reduction, it looks like this expression for solving distributivity. The tool also accepts contextual orders, but we don't expect them to be the common usage. We have 3 construction algorithms whose details can be found in the paper. To verify the one safety, the tool outputs CHC encodings of the automaton or grammar. Both are linear in size of the object. For the experiment, we use 3 different CHC solvers and take the best. We have 103 benchmarks in total, each labeled with a canonical reduction. 45% of the benchmarks were acquired from the literature, including those that search for reductions. We have 3 baselines: sequential composition and 2 versions of direct encodings without reductions. The line illustrated here is the best of the 3 baselines. The arithmetic benchmarks solved by the baselines are exactly those with a function summary in linear integer arithmetic. The 2 constructions that produce grammars show significant improvements over the number of benchmarks solved. Perhaps a little surprising, the construction that produces automata is slower, but is better at solving challenging benchmarks. Hypersafe is the best of the 3. The paper contains a detailed analysis of the 5 benchmarks that fail. In the end, I'd like to share a few things that we learned from doing this work. First, our reductions are syntactic in nature, but syntactic reductions can be powerful as well. There is an example in our paper, whose iterative version was cited in a previous paper as a challenging example that requires data-dependent alignments, but our method can do it easily, which is because we operate on expressive and unbounded syntax instead of manipulating the code. However, there do exist examples that truly require data-dependent alignments, and it would be interesting to investigate those. Last, canonical reductions, as well as their iterative analog, are useful. They may offer a practical solution to program alignments that sits between one fixed reduction, which has limited expressivity, and fully automated alignment search, which has limited scalability or requires user-provided abstraction in practice. Thanks. This is the end of my talk, and I can take questions.
Okay, question?
Okay, thank you for a good talk. I have 2 questions. The first is, when you require some user input as a spec, are you trying to using something like program synthesis to get a spec that can prove your goal? The second thing is, I want to make a confirm. When you are changing the pushdown system into the VP, are you seeking the decidability? Thank you.
Okay, so for the first question, we're not using program synthesis because the user encodes their reduction idea as a contextual order or a canonical reduction. But it may be interesting to investigate if it's possible to synthesize a scheduler. And I think I didn't fully understand the second question. Could you elaborate on that?
Okay. So you said that for some reason you didn't use the purely pushdown system, but you used something called VP.
Yes.
I guess are you seeking the reason why you do that is you are seeking the decidability from the system. Is that right?
Yes, and also VPLs are closed under intersections and complements, and all kinds of things makes the construction easier.
Okay. Thank you so much.
Thank you.
Okay, thank you.